Okay, welcome back to the first session after lunch. We have two talks in this session, one invited and one contributed talk. So we'll start with the first talk, which is going to be given by Professor R. Mahendiran from NUS, and he's going to be telling us about magnetoimpedance spectroscopy of oxides.
Okay, thanks, Chairman. Well, I'm not new to Bangalore, although this is the first time for me to come to ICTS. Okay, so I am from the National University of Singapore. So today's talk will be on magnetoimpedance spectroscopy of oxides. But I will be disappointing theorist. I am a hardcore experimentalist. But the interesting point is that what I'm going to describe, there is no theory so far. So in that aspect, probably it may be interesting for some of my theory colleagues. Okay, this work was mainly done by my former students, Amit Chanda, Ushnish Chowdhury, and Dr. Lee Yong Yang. Currently, they are not in my lab. Okay, I guess there are only few talks on oxides earlier, but I'm not sure that what are the materials that I talked about. But anyway, to try to introduce, I'm with NUS from 2005. Of course, I left IISc in 1996. So my lab focused mainly on oxide material preparation and studying the properties, starting with the magnetoresistance, multicaloric, magnetostrictive, and thermoelectric properties. And more recently, in the last few years, 2-3 years, I am shifting more towards the high-frequency magnetotransport in oxides. That's what I'm going to talk about today. And also spin caloritonics, which includes correlation between anomalous Nernst effect, Seebeck effect, and Hall effects, and magnetothermal power. And more interestingly, I'm trying to investigate the effect of microwave irradiation on synthesizing the sample as well as studying their properties. So this microwave synthesis has been used by chemists mostly, but not by physicists so far. So, well, I'm not going to show the results here, but I can say that it's quite promising because you can improve certain properties, particularly magnetism, dramatically by this microwave synthesis. Okay, so this is my lab, small lab. So we have all the necessary facilities needed for a good lab, starting from thermopower resistivity, which can be measured simultaneously, homemade ferromagnetic resonance spectrometers, 2 spectrometers, measurements for spin thermoelectricity, and then a PPMS for transport measurement, probe station, and the 2 more new additions include a cryogenic FMR spectrometer, which can work from 400 Kelvin down to 2 Kelvin. Also measure dilatometer, basically measure the magnetostriction. And then this is a furnace for microwave synthesis. It's a bit expensive furnace, about $50,000 USD, but it's working, it's giving good results. Okay, the outline of my talk today is as follows here. So first I will describe magnetoimpedance in metallic oxides. Don't worry about the formula, it may be complicated. And then I illustrate some examples in insulating oxides and compare what's going on in magnetic and non-magnetic bilayers, the work done by spintronics community. Fine. Well, I'm not sure what was talked about earlier, oxides. So starting with this, this talk mainly focuses on magnetoresistive oxide, particularly the manganese perovskites. Okay. So starting with that compound, lanthanum manganese oxide is an antiferromagnetic insulator. And it has only manganese 3+. But if you sort of replace lanthanum with the strontium, which is divalent, basically you introduce holes. That means you partially change Mn3+ into Mn4+, which has 1 electron less in the EG band. So basically the electron will hop from, the EG electron will hop from Mn3+ to Mn4+, and so on. But hopping is easier if the movements, these T2G moves, the spins on the T2G levels, they are aligned parallel. So ferromagnetism promotes itinerant electronic behavior. Okay, if they are disordered, then electron hopping is reduced. It can show a semiconducting-like behavior. So that is the basic principle. The mechanism is a Zener double exchange mechanism which drives ferromagnetism in this compound. As you can see here, that resistivity is the normal behavior of this doped manganites. So a semiconducting behavior, semiconducting-like behavior in the paramagnetic state, and then sudden decrease in the resistivity when ferromagnetism sets in. So you have a peak in the resistivity close to the TC. You apply the magnetic field, 1 Tesla, 3 Tesla, 5 Tesla, you can see that the peak decreases dramatically in magnitude and also shifts towards high temperature. It shifts because the ferromagnetic transition itself is shifted by 50 to 100 Kelvin under the magnetic field, which is not very common in metallic magnets. But the problem is that although this work, in fact, the first work was started in India by me when I was doing PhD in 1990s in IISc. Although this work, this magnetoresistance is colossal, in the sense that about 60 to 100% in a field of 30 to 50 kilohertz, the magnetoresistance at room temperature in a kilohertz range is very small, so 1 to 5%. So because of that, there is a decline in the interest the last 5 years. Okay, and most of the works published so far were measured with a direct current. But we know that the insulating like state in the paramagnetic state is due to small polaron hopping. So the question comes that, okay, what will happen instead of passing the direct current if I pass an alternating current? We know from because there are talks on, I think, multiferroic behavior. If you try to measure the dielectric constant, it may decrease with the increasing frequency. And also electron hopping can be increased in certain cases. So my initial point was to see that what happens to when I can delocalize the electrons in the paramagnetic state and then shift this temperature to higher temperature. So that was my initial motivation. And until now, there are not many reports on the AC magnetoresistance, either in this oxide or other materials, except for some amorphous ferromagnets, which I'm going to tell. So in a way that this is the AC electrical transport, but not extensively used so far. Okay, but I show that such a simple measurement yields to very exciting results. Okay, so my measurement setup, we work in a different frequency ranges, one from 100 Hz to 1 MHz. There's another setup which we use for today's talk is from 1 MHz to 3 GHz. So what we measure the electrical impedance of the sample, that is you pass the current through the sample, measure the resistance and the reactance simultaneously for different frequencies under different magnetic field. So the sample is this purple color basically here. So the current or the voltage is passed through the signal line, it goes through the sample and comes back to the impedance analyzer, which measures by RFIV method, measures the impedance of the sample, that is Z. Okay. So then you basically sweep the DC magnetic field, we see an electromagnet, what is shown here. So this is just a one port measurement. Okay, so what is interesting? First, the AC transport nowadays become more interesting because of what is known as the magnetocapacitance effect in multiferroics. Okay. So usually you take this multiferroic sample, cut into a form of a parallel plate capacitor, apply silver paint or silver electrode on the top and bottom, and subject it to an alternating voltage of few kilohertz, and measure the impedance. So the impedance is 1 over Z equals to 1 over R plus I omega C. So from that you can get the capacitance. If you apply the magnetic field, the capacitance will vary. For example, this is a ferromagnetic insulator, bismuth manganite. So the capacitance changes dramatically around the Curie temperature. So understanding the exact mechanism of magnetodielectric coupling is important. But if the material is not highly insulating, what you measure is wrong. But that many people don't report. Until now, even now, it's very common to report only the change in delta. Change in the dielectric constant, not the change in tan delta, which is the connector of the phase, which also involves epsilon double prime. But many papers, in this field, there are many papers which are not trustable in that sense. But on the other hand, in 1994, there was a work on what is known as the magnetoimpedance in amorphous ferromagnet. Okay, these are metallic ferromagnets, either completely amorphous or nanocrystalline materials, so which can be considered as a combination of the resistance and the inductance series, Z equal to R plus I omega L. So here the impedance, as like here, the impedance, when you apply the magnetic field, the impedance changes rapidly at low field and then try to saturate. So this is the magnetoimpedance effect. Here, it is not necessarily that the resistance change, the impedance change comes from the resistance change, but it's coming from L, that is the inductance of the sample is changing. Okay, so this is the giant magnetoimpedance effect, which I think the community working in amorphous materials, ferromagnets, so they're familiar, but not the oxide community. Okay, because I was looking at multiphoric behavior long before and found some problem with my own experiment. I tried to understand what was going on, so that's how I started. So this is one of the compound today I'm talking about. It's a praseodymium strontium manganate with a 40% hole doping. Forget about the other details. So this compound, as you see, this is the DC magnetization, which shows that there's a ferromagnetic transition, there's a rapid increase at load field, ferromagnetic transition, then there's a, within the ferromagnetic state, there's an anomaly around 100 Kelvin. So this anomaly comes because of a structural transition from orthorhombic to the mixture of orthorhombic and monoclinic phase, which also was confirmed by differential thermal analysis, or like what I've shown here. Okay, so this is the magnetization. How about the resistivity? The resistivity, DC resistivity, is something similar to 1 megahertz. You see a small hump here at the TC because the sample is polycrystalline, grain boundary also contribute. Then you see another bigger peak, maximum here. But when you increase the frequency, you can see that in zero field itself, when it's 10 megahertz, the zero field itself, suddenly the resistance increases here. Okay? And that exactly coincides with the ferromagnetic transition. Thus, a resistance shows an anomaly at high frequency, even in zero field. Then you apply a magnetic field, 0 to 1 chloride. 1 chloride is still a small field. So you can see that from even for 300 iostate, the magnetoresistance, there's a remarkable magnetoresistance here. This feature has now gone. Okay. So thus, the AC resistance here already shows the magnetic anomaly, which is not seen in the DC resistance. Now go for the reactance. The reactance shows a sudden jump here, as I expected, because if the reactance is connected with just the inductance of the sample, the inductance is connected with the permeability or the susceptibility. So a ferromagnetic compound will show a jump at the TC, the susceptibility. So it shows a jump, then you can see that actually that it decreases, then there is an anomaly at low temperature, around 100 Kelvin, which is exactly what we see in the DC magnetization. Thus, the AC reactance here clearly reveals the magnetic behavior. Okay, of course, at high frequency, I can see in both the R and X part. So that AC transport mimics the behavior of the AC susceptibility. Okay, this is a very simple idea. But you search the literature, you won't find many papers, probably not more than 3 or 4. And out of 3 or 4, maybe 3 from my group. Okay, that's because people probably have not thought about using this simple experiment more effectively. I don't know why. Okay, now I go for the high frequency part. Again, take the same compositions, praseodymium, now only with the praseodymium and neodymium. The difference is that if it's the praseodymium, then I have a ferromagnetic transition at room temperature. If it's the neodymium, the ferromagnetic transition shift to low temperature, 270 Kelvin. So this sample is paramagnetic at room temperature. This is ferromagnetic at room temperature. Fine, both the compounds show an insulator to metal transition, and the temperature is changed around the Curie temperature. And this is the magnetoresistance. You can see the magnetoresistance is for 1 Tesla. It's 6% in the ferromagnetic sample and reduces to 2% in the paramagnetic sample. Okay, this is a common behavior anyway in manganites. Now, what is interesting? This one, going for the AC transport. Okay, so unfortunately, we can currently do this measurement only at room temperature because we have to take care of some experimental problem and you do as a function of temperature. So this I just compare here on the top part, the AC, this is MR AC means that the AC magnetoresistance at 0.1 gigahertz, you can see it's a negative. This is the paramagnetic sample. You go for 1 gigahertz, then you start seeing a peak here close to the zero field. You go to 3 gigahertz, you can clearly see that the peak has shifted up. Okay. So the magnetoresistance has changed the sign from negative at low fields, low frequency, to positive at high frequencies. So there's a sign in the change of the magnetoresistance at room temperature, although the sample is paramagnetic. Okay, so this is a 3-dimensional graph where I vary the frequency from 1 gigahertz to 3 gigahertz. You can see that clearly the peak, the central peak now splits into 2 peaks and it's beautifully shifts upward. Okay, and the reactance shows a corresponding change. Whenever there's a sudden increase in the resistance, the reactance shows a dip. Okay, so what is this reactance? So that's what we will see. So the point here is that we could get a magnetoresistance of 2% at 1 Tesla with a DC current, but we can get about 5% in a field of 2.5 kilohertz state. Already in the paramagnetic state itself is, the magnetoresistance is larger than the DC resistance. Okay, now I go to the ferromagnetic sample. This is the room temperature ferromagnetic sample. So I compare here the paramagnetic sample, which I just mentioned before, and the ferromagnetic sample. You can see that qualitatively they look similar. Both the cases I have a zero field. There's a peak in zero field. For low frequency, when you increase the frequency, the peak shifts upward. But you can see that there's a much larger separation between the two peaks here. I say that the canal is bigger in the case of paramagnetic sample, but it's more sharper in the case of ferromagnetic sample. In addition, you can see that the reactance itself shows a very interesting change. You have a flat behavior here, and then the dip here. Whereas here, there's a zero field itself, there's some future, and then there's a dip here. So very clearly, the ferromagnetic sample and the paramagnetic sample shows a very different behavior. Okay, this was not expected in the beginning. Okay, well, we try to correlate the results. So I have a magnetoresistance, which is a red color, magnetoreactance in blue color here. But if I try to take the derivative, dmr by dh, you can see that the peak in the magnetoresistance coincides with the dip in the magnetoreactance. So it's just sufficient to measure one. Of course, in experiment, we can measure both. That's in a way advantage. So this is what is shown here, magnetoresistance now with for few selected frequency. We do a fit as a combination of two Lorentzians, which is very common nowadays for the people working in bimetallic ferromagnets. They have to use such a formula to describe the inverse spinel effect. We'll go into the detail later. So we could fit it from this, we can get the resonance field and the line width. Okay, the resonance field here means that where the magnetoresistance shows a peak. Okay, this is the resonance field. And then line width is from this peak to this peak. Okay, so what I'm telling that the future, what I have seen now, this peak is due to what is called the ferromagnetic resonance or electron spin resonance. Okay, but of course I have to prove it as an experimentalist, not to jump into theory and to come to the conclusion. Okay, before that, I'll take this sample now. Instead of praseodymium, neodymium, I'll take lanthanum because lanthanum compound has the Tc 360 Kelvin, the pure compound. If I replace manganese with the gallium, I dilute ferromagnetic interaction, and then I can push the Tc down to low temperature. So as you can see that as a function of gallium content, basically I'm going from this all ferromagnetic sample this to a paramagnetic sample. And this sample has the Tc which is very close to the room temperature. As you can see here, you can also start seeing some wiggles here. Okay, in this particular compound. That is because I'm able to detect both paramagnetic resonance and ferromagnetic resonance in the single sample with a very simple technique. Okay. Well, I won't go into the detail. You can see the very clear difference coming here. Paramagnetic samples always shows a big width compared to the ferromagnetic sample. You will come to know later why it is so. But interesting point is that the magnetoresistance now is 80% in a field of 1 kilohertz state. Whereas you need 7 Tesla to get 7 or 9 Tesla to get that value when you use the direct current. So that is something very exciting. And still it has been overlooked. Not many people have done similar work. Okay, now come to the understanding. Did I understand the results? Unfortunately, not completely. This is where probably theory colleagues can help. But as an experimentalist, I try to see what could be the possible origin. One simple explanation that you are passing an AC current through the sample, or increasing the frequency of the current. What should happen? What should happen from PhD students? At low frequency, the current try to flow uniformly through the sample. Usually use the lock-in amplifier, around 10 kilohertz or 100 kilohertz. But when you increase the frequency, the current will try to flow only on the surface of thickness delta, which is known as the skin depth. Okay, those people working on superconductivity, they will realize it's important. Okay, so this skin depth plays a very important role at high frequencies. Okay, which can be written as now, if the skin depth is delta equals to square root of 2 rho over omega mu t, where mu subscript t stands for transverse permeability because it's connected with the permeability in the transverse direction. So the impedance at a high frequency can be simply written in this form, square root of omega mu naught mu t and divided by 2 rho, basically this one. However, the permeability itself at high frequencies is a complex number. There's just a real part and imaginary part. Real part is connected with the the magnetic behavior, and imaginary part is connected with the absorption in the material, okay? So if you substitute this one, you can get that the resistance is proportional to square root of modulus of mu t plus mu t double prime, and the x is, square root of modulus of mu t minus mu t double prime. So basically, the resistance will be dominated by the field dependence of mu t double prime. Because remember that mu t double prime is connected with the electromagnetic wave absorption, okay? Thus, even if the resistance itself is not changing due to other scattering mechanism, the change in the high frequency permeability is imposed now on the resistance and the reactance spots. This is what we seems to be finding, okay? To be further, go further, this is a conventional ESR spectrometer used in many laboratories, where you have the DC magnetic field. The sample is somewhere here, is the microwave source. So it supplies the microwave, which is basically perpendicular to the DC magnetic field. So there's a Zeeman splitting when you increase the magnetic field. So then when the transition takes place between these two Zeeman level, because of the AC field, then you have a peak in the power absorption, which when you use the lock-in technique, you get as a dP by dH. This is called the ESR spectra, okay? The same approach here. So current, AC current this way, the AC magnetic field is in this direction. So basically the RF field is transferred to the DC field. Same configuration, very simple experiment. And probably the same thing happens here, okay? Except that now the power absorption is proportional to the real part of the impedance times the square of the RF magnetic field, whereas here it's proportional to omega mu double prime h square half. Again, I remember the real part of the impedance is, even in this case, affected by mu double prime, except that mu prime also get involved. Well, so there are few models which were actually developed for other material, like amorphous materials. So they told that this paper particularly came in '96, they showed that the calculation for the magnetoimpedance of a ferromagnetic resonance or ferromagnetic resonance are basically equivalent. And this paper tried to tell that the transverse susceptibility can be considered as the low frequency ferromagnetic resonance, okay? So still this paper get more attention from the other community, but not from the oxide community. For the students who are not familiar, the electron spin resonance is the resonance field or the resonance frequency is proportional to the DC magnetic field, and they will show linear behavior, okay? Whereas for a ferromagnetic sample, you have this nonlinear behavior, basically square root of H resonance plus HK and so on. So this is the main difference between the ferromagnetic and paramagnetic sample when you measure the spin resonance, okay? So here is the only one paper which I came across, published in 2006, where they used this impedance technique. They did not measure real and imaginary part, but only total impedance. They found the behavior which is similar to us. Up to some frequencies, the peak shifts very slowly, then it shifts rapidly. So where this rapid shift starts is the region corresponding to the impact of the dynamical magnetization, that is the ferromagnetic resonance dominating the measured impedance. Whereas here, it's anisotropic effect dominates. Now, being an experimentalist, I try to be more careful. So what's really happening to my sample? Okay, should I necessarily pass the current through the sample? Okay, or should I use some other technique? Okay, well, so unfortunately, I could get one vector network analyzer. So what we made a simple idea is that we put the sample, we took a copper strip, simple copper strip, and bend it in the form of a L shape like what is shown here. The sample is inside, it's insulated from the copper strip, and we measure what is known as the scattering parameters using this vector network analyzer, which can be converted into microwave power absorption, like del P. You see that this is exactly what I have shown you by passing the current through the sample. So this means that the current passing through this strip produces an RF magnetic field, which interacts with the magnetization of the sample itself. And that has a reflection on the impedance of the strip. That's what you show here. So basically is the electromagnetic wave absorption, okay, for ferromagnetic or paramagnetic resonance. Further, to go one step ahead, okay, you don't believe this result. So use a commercial equipment, this is about 110,000 USD. Okay, this is a cryo-FMR, which can go from 400 Kelvin down to 10 Kelvin. What you do is that you place the sample somewhere here between this Helmholtz coil. So basically you pass the high frequency current through the signal line, and then it creates an RF magnetic field around this, which will interact with the sample, and the spectrometer, with a very, very expensive spectrometer, measures dP by dH, that is the power derivative, power absorption derivative. Okay, this is what we compare the results. Okay, this is from the AC magnetoresistance done with a very simple setup. Okay, where I show that this behavior is very linear for this paramagnetic sample, and this is this broadband electron spin resonance measured up to 10 gigahertz using the commercial spectrometer. You see this behavior nicely. It both show the same results. So we do all the fittings. I won't go into the details of this. Okay, now thus I have proven that it's what I am seeing is really due to electromagnetic wave absorption, basically microwave absorption in the sample, either due to ferromagnetic resonance or electron spin resonance, but measured by electrical method, a simple electrical method. Now, can I use this for the insulating sample? I cannot pass the current through the sample. So what should I do? Okay. Think carefully about it as an experiment. It's what idea you can get. So again, use the simple idea. So I put the sample inside this, what the microstrip we've made. And this is an insulating sample called lanthanum nickel manganese. This is a double perovskite with a TC of 270 Kelvin. Now we can see the clearly short peak compared to the previous samples, okay, which is shifting with the frequency. And this is due to electron spin resonance in the at room temperature in the sample. Okay. Now I go still further. Again, I compare this result. Let me not go into the detail. This is the commercial. This is the results from the commercial setup. Here I compare from these two setups, the magnetoimpedance and the commercial setup, and I show that actually they really follow a linear behavior with some, about 1 to 5% error. That's fine. Okay, which really nicely match. But now, even instead of going to this oxide, if I take a commercial sample, which is a very standard ESR marker for chemists and physicists, it's called DPPH molecule, which has nitrogen here. There's a free radical. This one electron travels around that, and this is an insulating material. Okay, I use this technique again to measure this impedance. You can see that now we get a much sharper peak than the oxide samples. So beautifully, again, it follows the ESR relation. Okay, this will be the last one, last two slides. Well, I still go on at, okay, why should I have a strip? After all, if the idea is that basically you pass the current through the strip and make the electromagnetic field filled by the sample, can I do some other trick? Okay, well, so it's better that I coat the sample with a silver paint, or basically deposit with the silver electrode, but I didn't have the facility, so I just took a silver paint, which you normally use any students use. So I just apply the silver paint on the top of the sample and on the side, so that the current, RF current, is flown through the silver paint through the sample, and then measure the impedance. This is a very dirty technique, but it gives an excellent result. Exactly the same result as what I got previously with the strips. Okay, and thus, okay, now I can even measure the insulating sample with this simple technique. So this is what, as an experimentally, a very serious experimentally, it excites me. When you use a very simple method, even if you are using the old sample, it's fine, but a simple technique gives rise to some results which can be reproducible by other methods. Well, so we also measured for thin film. This is called IG, is an insulator, and also ceramic sample. We compare the result. I won't go into the detail, which are already published in this paper. You can see where this is the ferromagnetic oxides. We can nicely see the Kittel's behavior in the samples. Okay, let me skip this. The last slide is on a different compound. This is the inorganic organic complex. Okay, I didn't know anything about this material, so my chemistry collaborator wanted to study magnetoelectric coupling in this material. I was the only one in NUS having facilities to measure magnetoelectric coupling in a simple measuring a different way. So we took this compound, we measured this at room temperature. This is an insulating compound. This is a it shows the ferroelectric ordering at low temperature. Okay, you can see that beautiful peaks. And nicely follows the linear behavior. And thus I am very happy. With a very simple technique, I am able to probe electron spin resonance, which I never studied during my PhD. Okay, so I'm quite happy with that. So there are several papers now will appear with my collaborator from chemistry on this metal inorganic work. Okay, now the last two slides. There are many papers recently. I think there are not really spintronics community people here except Satyajit or somebody else, where people study a ferromagnetic metal and then they have a non-magnetic metal with a high spin orbit interaction. Okay, so what they do is that they pass high frequency current through or subject this material. They put in this material inside the microwave cavity and then subject to the RF magnetic field, which basically the current in this sample, the charge current in paramagnetic metal like a platinum, induces spin current which flows through to this permalloy and makes the magnetization to precess. Okay, so this is, and then it is detected as a voltage at the end in the setup. So basically, this is the FMR. This is of this sample in using a microwave cavity, and this is measured with the DC voltage is measured, which exactly when you take the derivative, which shows exactly the same behavior. So this is the electrical detection of the magnetization or the ferromagnetic resonance in bimetallic layer, which are very popular among spintronics community. Okay, and also not only ferromagnetic metal, but also Ig is an insulator. Platinum is a metal. So again, you pass the RF current through the platinum. Current will not flow through the Ig, but it will induce a spin current in the ferrimagnet. It can make the ferrimagnetization of the ferrimagnet to oscillate, and it will induce a backflow of current in the Ig, the platinum, and then you can measure the voltage, which basically mimics the magnetic resonance, ferromagnetic resonance of the Ig. So this type of studies are very common nowadays among the spintronics community. But what we measure in our case is that not the DC voltage, because the DC voltage, what they measure actually has many contributions, okay, which include the spin rectification, which comes because of nonlinear coupling between MR and the RF current, and then inverse spin-Hall effect, the spin transfer effect. So one has to do a very careful experiment to distinguish this where exactly from this DC voltage comes. But people have not measured the AC voltage except for one paper. Okay, so in our experiment, we are measuring basically the AC impedance, basically measuring the AC voltage, that we may be able to pinpoint clearly that what is the driving mechanism of this DC voltage in these magnetic bilayers. That's what we want to do. So we are going the right direction. So the last slide. Okay, all people what studied is that you can induce the DC voltage due to inverse spin-Hall effect in bimetallic layer. Okay, here we are a bit crazy. We have the bulk sample here, forget lanthanum, strontium, manganate, something. So this is the dP by dH. And what we measure is in the bulk sample itself, we measure the voltage. And at least not for all the sample, for one sample very clearly, there's a ferromagnetic resonance here. And then the DC voltage shows a clear anomaly at the same magnetic field where there's a peak occurs. So this is like the inverse spin-Hall effect in a bulk worst ceramic material. Okay, we haven't understood yet what really causes this. Thus, to conclude, the ACMR is much larger than DCMR. These materials, not necessarily in this material, probably in other materials also. And ACMR shows the fingerprints of ESR and FMR, which are also verified by two independent techniques. One is the microwave VNA-based microwave power absorption. Another is the commercial broadband spectrometer. So this is a technique still less exploited. It can be used for domain wall resonance and the domain mode resonance in non-saturated region, which is not possible by other methods. But then here comes the theory. All I'm arguing is that probably it is the oystered field. You're passing the RF current, it is the oystered field which instruct with the magnetization of sample. Maybe I'm wrong. Okay? This could be other possible reasons, like spin transfer torque or spin orbit torque. So we have to investigate other materials, particularly not bulk ceramics, which is difficult to get in nature, but the same thing you do with the thin film, get the results, you can get in nature most likely. So we have to investigate thin film samples for this, and then little work on the AC spin-Hall effect, even on the bimetallic layer. So whether this has anything to play. So that the main question here is that for theorists, what really causes this change in the impedance? Is the oystered field or spin transfer torque? So just like to mention that, I think there's a paper which just appeared last week there they used the STM, scanning tunneling microscope, to study electron spin resonance I think in one of the not graphene molecules, where they found that actually spin transfer torque plays a very important role. Okay, this is from a work from the ETH Zurich group. So still it is a open question. You know, if some of you are interested in formulating the theory, probably you'll be the first person to explain. Okay, I'll leave it as an open question. Okay, okay, that's all. I mean, time. Yes. Sure.
Hello. Yeah, very interesting work, sir. So my question was in the material where you were comparing both bulk and thin film, I think YIG. So do you see any effect of strain or dimensionality in your results for the thin film part?
No. Thin film, we did investigate only 2 thin films because these thin films are not under my control. I got it from my Japanese collaborators. So I did not investigate.
Okay, okay, sir. Thank you.
And also because if I put the silver paint on their MB grown film, they are not happy. Okay, I have to convince them, I'm going to spoil your film, then it's okay. You can give to me. Yeah. Yeah.
Thank you, sir, for the talk. I have 2 questions. One is, in bulk, does it have any broken inversion symmetry? The last slide that you were showing.
No.
So it's completely symmetric. So
Yes.
there isn't any possible of RASPA interface or something like that.
No, not at all. This is the bulk material.
Yeah.
And this manganese doesn't show inverse broken symmetry.
And the second is, how do you control the polarization of the electromagnetic wave in presence of a AC field? I mean, it should match the phase of the ferromagnet, right, to show the FMR. And you are applying AC field, so does it affect the polarization of the incoming wave or not?
I cannot answer to your question clearly right now. I have to think about it. Yeah. Yeah. Even even at 350, I can get 80% my resistance now with the AC method. When I say room temperature with 300 Kelvin, but what I'm telling that I can get magnetic resistance even much above room temperature. And not necessarily in this oxide, some other the other alloys also, usual alloys and so on. We are trying to investigate a wide range of materials now.
Further questions? If not, thank the speaker once again.
I think one question.
Sorry.